52 factorial, a number so big it is said to be bigger than the number of atoms in the universe. A statement reiterated in YouTube videos, blog posts, and TikToks, all the right scientific sources, is the number of arrangements a deck of cards can be in. Shuffling a deck of cards will, however, not produce this many possible arrangements. Imagine we have a deck of 52 cards. We then make a cut somewhere along the deck, resulting in two piles, which are not necessarily equal in size. Shuffling these are then essentially consecutive choices between two options, until a pile runs out. This means we have at max 2 to the 52nd possible arrangements per cut. This can be illustrated with a tree structure. For a manageable example, take two piles of 2 cards, coming from a deck of 4. A branch to the left is taken from the left pile, and a branch to the right is taken from the right pile. Of course, as soon as one pile is empty, the only option is to choose from the remaining pile until that is empty as well. So come with me on a discovery of the mathematics of card shuffling involving dead ends, unpleasant hindsight, and a cool induction proof. So let's look at some patterns. The first would be the one we already found. When one pile is empty, there is only one option left. Trying to extend this pattern, we get that as soon as we take from the pile with one card left, we're back at the previous result of exactly one option left. This gives us x plus 1 arrangements for x cards in one pile and one card in the other. In fact, the following pattern holds for x cards in one pile and y cards in the other. The following recursive sum expresses the amount of arrangements we can get in a shuffle. Then looking at a pile of x cards and another with 2 cards, we get the following sum, which we can split like so, having a term that collapses to x plus 1 and a term which is the famous Gauss sum. We then keep increasing the right pile and get the following results. We quickly spot the denominator being the factorial of y, then making a pyramid of the numerator is this. With the differences added, we can see patterns for each column, and guesses for column expressions can be made. In fact, this relation holds as far as I checked. Here I was stuck a solid couple of days. All expressions were still specific for a column or something else. I was missing the grand unified theory of shuffling x and y cards. Of course, it is manageable to just recursively calculate up to 52 cards, but that's just not cool. I finally gave in and took a wild guess on a factored expression. And what do you know? It is identical as far as I've checked. So this is a solid guess. By now you're probably thinking, this guy is doing a lot of wild guessing for a math video. To which I say, absolutely. And later I will show you a way of either proving or disproving the guess. And disproving is often easily done with a counterexample, that is, finding a single case that makes the guess fall apart. We get this formula for the shuffle, and this reduces to the following formula. You can take a minute to convince yourself, or you could ask Wolfram Alpha. Also, if you squint your eyes really hard, you can't really see the difference. If you think this looks familiar, you're absolutely right. It is the choose formula. This would be cool and all if there wasn't a very simple way of imagining shuffling cards that would lead directly to this realization. Take a deck of n cards, cut this into 2 piles of r and n minus r cards. We then pick r spots in the new deck of n cards, And since the piles aren't shuffled internally, this is exactly in choose R. I mean, come on. Swings and roundabouts are the bane of my existence. Guesses and obviousness in hindsight is great and all, but we have a definition and a guess for a solution. And we really need some confirmation we have been burned before. Our weapon of the day is the induction proof. For this, we need a base case, a hypothesis, and an induction step. Doing the base case first is usually a good idea, as this is very quick, and it would be nasty if it turned out to be a counterexample. But I have uncapped hubris and zero respect for my own time, so let's grab this induction step by the horns. Our hypothesis is that our function f of x and y is in fact x plus y choose x, which when inserted into our definition gives the following. And if this is true, then the following value of x can be simplified as follows. Bring out the last term of the sum, then we substitute the remaining sum, and then it's just a matter of shuffling factorials around, and we see the formula checks out. Now we have, if for any number of cards this is true, it will be true for one more card. This is essentially a mathematical line of infinite dominoes, so we quickly check for the exciting case of shuffling a single card. And of course, 1 equals 1, it checks out. But let's get back on track. I mentioned in the beginning that we cut the deck somewhere, and this is important, as this will greatly increase the amount of possible arrangements, bringing us ever closer to beating the number of atoms in the universe. In this first shuffle, essentially one cut can only produce one arrangement identical to any arrangement in any other cut. And this shared arrangement is exactly the original arrangement. To convince ourselves of this, let's look at neighbors around the cut. These will swap in order in all arrangements except if we go through all of the bottom pile, after which there is only the other pile to take from, leaving us with only one arrangement preserving the cut neighbor order. And since it is only this cut that can break this neighbor order, we have n choose R minus 1 for all cuts R plus the original arrangements as the total number of arrangements possible. And shout out to Pascal's triangle, where we're essentially summing rows and subtracting n. And the beautiful thing about this is that each row sums to 2 to the nth, giving us 2 to the nth minus n arrangements. So we have 4 quadrillion, 503 trillion, 599,627,370,444, or 4.5 times 10 to the 15th, if you want the less sensational. This is kind of a lot, but nowhere near 52 factorial, which is 8.07 times 10 to the 67th, which is also a lot, but a lot more a lot. We will need multiple shuffles to beat the number of atoms in the universe. Having multiple shuffles could trick us into thinking we just do powers of the arrangements after one shuffle, but we quickly realize that we must be bounded by 52 factorial. Okay, new idea. Instead of counting arrangements after some number of shuffles, we can figure out how many shuffles we need to arrive at 52 factorial. If we have a deck of 52 cards and we do a cut, we visualize it as so. Without shuffling the cut into an arrangement, we leave all shuffles being possible. And after a shuffle, A second cut will then look as so. Of course, a second cut can limit the number of shuffles beforehand allowing for this cut, but that's okay. A shuffle from here would then essentially have 4 piles to draw from. So we just want to cut until we have 52 piles to draw from, allowing every single arrangement to be possible. This is quite simply the ceiling of the logarithm with base 2 of 52, which is 6. Of course, the cuts could be made to create very uneven subpiles, but since we consider all cuts possible, we're interested in the smallest number of cuts completely dividing the deck. If 52 factorial is bigger than the number of atoms in the universe, then it could be possible that we surpass before we hit 52 factorial. So 52 factorial isn't exactly bigger than the number of atoms in the universe, so no amount of shuffling will give us more arrangement possible than this.